They were not killed slowly. They were not taken by time. One instant the world was full of life, forests breathing, oceans humming, the heavy footfalls of giants that had ruled the land for tens of millions of years. The next instant, the sky answered with a rock. 66 million years ago, at the geological stroke that marks the end of the Cretaceous, something walked out of the dark between the planets and struck the Earth with an energy that no life form had ever seen. The impact was not a rumor or a faraway whisper of disaster. It was a single, catastrophic signal, a thunderbolt of heat and pressure, a storm of molten rock and blinding light, the kind of violence that rewrites geology and biology in one incandescent breath. This is the story of that strike, the Chicxulub event, and of how an object not much larger than a mountain changed the trajectory of life on our planet forever. To grasp the magnitude of what happened, imagine a sphere of stone 10 to 12 kilometers across, roughly the width of a small city, moving at tens of kilometers per second. Kinetic energy scales like the square of the speed. An object like that, hitting an ocean-bordered shelf, delivers an explosion unlike any volcano, an instant release of heat and momentum equivalent to billions of atomic bombs. In the blink that followed the collision, a transient cavity the size of a small nation ripped open in the gulf of what is now the Yucatan. The ground itself momentarily behaved like water, heaving and slumping, collapsing into a ringed depression hundreds of kilometers across. The feature the impact left beneath the northern Yucatan, an immense, buried saucer of rock and melted stone, ringed by fractured peaks, is what geologists now call the Chicxulub crater. It is, by any measure, one of the great scars on Earth's skin. But the crater is only the beginning. The violence of the strike radiated out in waves. Not only seismic waves, but atmospheric, thermal, and oceanic waves that moved faster and farther than anything living had evolved to survive. Close to the impact, whatever stood within tens to hundreds of kilometers was simply vaporized trees turned to ash, animals scorched into shadows, coastal ecosystems scoured by the first monumental tsunamis. A wall of water, thrown up by the initial blow, raced outward with an unstoppable momentum, slamming into shorelines and washing inland in a cascade of salt and ruin. In places along ancient continental margins, sediments record the footprints of these mega tsunamis, ripples and deposits that tell the story of water mountains traveling hundreds of kilometers from their source. Even regions that escaped the direct thermal blast were not safe. The impact hurled an unimaginable volume of rock, soot, and vapor into ballistic trajectories. Molten ejecta streamed high into the atmosphere and then roared back down, each incandescent fragment reheating the air as it re-entered, a global pulse of heat that likely ignited widespread fires. Microscopic soot and sulfur compounds lofted into the stratosphere, where they could remain suspended for years, forming a planetary veil. Sunlight, once soft and generous, was stolen. Photosynthesis faltered. Plants, plankton, the very base of the food web, all the green things that convert sunlight into life, found themselves robbed of light and choked by acid and ash. The planet slid into a kind of darkness not measured in hours, but in seasons. The effect is often described as an impact winter. And it was this prolonged loss of energy from the sun that did the most damage to ecosystems that depended on abundant, steady sunlight. If you try to picture the first days after the impact, do not imagine a single form of terror. Picture instead a stacking of catastrophes, one driving the next. The mechanical shock, earthquakes of magnitudes well beyond any recorded by humans. Ruptured continental shelves and may have triggered tsunamis on multiple ocean basins. The heat pulse ignited fires that turned landscapes into long, glowing seams of ash. Atmospheric chemistry shifted as sulfuric aerosols formed from vaporized gypsum and other minerals, leading to acid rain that damaged leaves and poisoned freshwater habitats. Pelagic food chains collapsed as marine phytoplankton, deprived of light and coated in chemicals, crashed in abundance. On land, herbivores that depended on leafy energy could not find enough to eat. Without herbivores, predators starved. For many clades, the hits were simultaneous and merciless. The evidence for this chain of ignition is both global and specific. Around the world, at the thin sliver of rock that marks the Cretaceous, Paleogene boundary, geologists have found an anomaly. An unusually high concentration of iridium, a rare element on Earth, but comparatively common in some kinds of extraterrestrial rocks. That global clay layer, the iridium anomaly, is the fingerprint of the strike smeared across continents. In addition, shocked quartz, spherules of glass formed from molten droplets, and other telltale ejecta have been discovered at the same stratigraphic horizon in sites from Europe to the Pacific. Together, these lines converge on a single, disturbing conclusion. A very large bolide struck the planet at the end of the Cretaceous and injected enough energy and material into the environment to provoke a mass extinction. The biological toll was immense. Estimates vary, but the extinction removed a large proportion, perhaps 3/4 or more, of all species on Earth. Non-avian dinosaurs, the great terrestrial rulers for more than 150 million years, disappeared from the fossil record. Many marine reptiles, ammonites, and myriad plankton groups were also extinguished or dramatically reduced. The pattern of death was selective, not random. Small, burrowing creatures, animals with generalist diets, and organisms able to exploit detritus or marine planktonic refuges fared better. Birds, the living descendants of one dinosaur lineage, and early mammals, small and adaptable, quietly persisted in the ecological rubble. The extinction reshuffled the deck of life and created the ecological vacancies that mammals and later humans would eventually exploit.
Yet, even the broad outline above hides a richer, more complex truth. The Chicxulub event did not unfold in a vacuum of time. The late Cretaceous was a world of dynamic change. Sea levels rose and fell, continental arrangements drifted. And at roughly the same time, the Earth was also experiencing one of the largest volcanic provinces in history. The Deccan traps of what is today India, pouring basalt and gases into the atmosphere for hundreds of thousands of years. For decades, scientists debated whether the asteroid strike was the sole executioner or whether it acted in concert with volcanic climate forcing and long-term environmental stress. Recent syntheses suggest the reality is not a binary either, but a more nuanced interplay. The impact provided the instant, global kill switch. The volcanism and other environmental stresses may have primed ecosystems to be more vulnerable. The precise choreography remains an active field of research, part detective work on a planetary scale. Our modern understanding of where the killer came from has also evolved. The object that carved Chicxulub was not a terrestrial phenomenon, it was a resident of the solar system. Geochemical fingerprints in ejecta suggest the impactor was a carbonaceous chondrite, rich in volatile materials, implying it may have originated from the outer reaches of the asteroid belt, or even from beyond Jupiter, before being nudged inward onto a collision course with Earth. This is not just scientific trivia. It connects the catastrophe to the chaotic dynamics of our planetary neighborhood, reminding us that Earth's fate is sometimes determined by forces that once resided in the cold calculus of orbital mechanics. Recent isotopic analyses and trajectory models have argued for an origin of the object in the outer solar system, a rare and consequential provenance for such a devastating impact.
Incredible.
If we step from the immensity of the event back into a human register, into the language of storytelling and sensation, the impact has the same narrative economy as a myth, a sudden elemental horror that rearranges the world. But the story also has a slow, patient scientific epilogue. For many decades, the Chicxulub crater lay masked beneath sediments and sea. It was first hinted at in oil company magnetic surveys in the 1970s, and then gradually revealed by geophysicists and field geologists who read the anomalous gravity and magnetic signatures like a doctor reading a pulse. Eventually, drill cores and seismic reflections confirmed the buried ring and the immense structure beneath the Yucatan. In recent years, dedicated scientific drilling expeditions into the crater's peak ring returned continuous cores rock that carries the memory of the impact and its immediate aftermath. These cores have been a revelation. They show layers of impact melt and breccia, shocked minerals, and traces of the environmental fallout. They also reveal something unexpected and strangely hopeful. The collapsed peak ring hosted a long-lived hydrothermal system in the aftermath of the impact, a kind of steaming, mineral-rich oasis that for thousands of years after the strike could have provided habitats for heat-loving microbes, a brief, local cradle of renewal amid global catastrophe. The geology does not only record death, it keeps a ledger of recovery, of niches where life found a way to reassert itself. This duality, annihilation, and nascent recovery is crucial to understanding the long arc of the Chicxulub story. In the first catastrophic months and years, the dice were against life. Food webs collapsed, climates cooled and then oscillated, and many lineages were terminated. But Earth systems did not stop. They reorganized. In the oceans, microbial communities began to re-establish themselves in the crater's shadow, and over millennia, planktonic ecosystems recovered and diversified. On land, the emptied ecological theaters allowed opportunistic and adaptable groups to radiate into the vacated roles. The world that emerged in the Paleogene was not the same Earth as before. It was a planet with new winners and losers, new opportunities, and a biosphere rearranged by a single cosmic moment. If the first chapter of the Chicxulub story is instantaneous violence, heat, shock, and an atmosphere full of falling fire, the second chapter is quieter, longer, and just as consequential, a slow, patient rewiring of Earth's biosphere. This is where the anatomy of extinction becomes legible, where the winners rise, not because they were lucky in a single moment, but because their bodies and lifestyles happened to fit the new, brutal checklist of survival. The early months and years after the impact were a time of dramatic simplification. Ecological specialists, those animals and plants exquisitely tuned to particular climates, diets, or habitats, found themselves without their narrow footholds. The great herbivorous dinosaurs, many of which had evolved enormous selective guts for processing specific plant communities, faced a sudden famine. Gews of angiosperms, the flowering plants that had diversified across the Cretaceous landscape, were smothered by ash or starved by darkness. Without a steady green engine beneath them, large herbivores could not sustain their metabolisms. Without herbivores, the multiton predators that depended on them collapsed in turn. The fossil record, imperfect as it is, shows a vanishing act. Skeletal worlds, once crowded with niche specialists, fade into fewer, smaller, and more generalized forms. Yet in the rubble, there were refuges. The ecological insurance policies of life were small, humble, and often boring. Burrows, shells, fat stores, omnivorous diets, and the ability to exploit detritus. Creatures that could hunker down beneath the soil until sunlight returned. Many small mammals, certain amphibians, and some reptiles gained a statistical advantage. Aquatic ecosystems exhibited their own selectivity. Planktonic organisms dependent on photosynthesis crashed where light was cut off, but deeper water and detritus-feeding organisms sometimes persisted. Some bivalves and foraminifera plummeted in diversity. Others endured in pockets where sediment or chemistry buffered the worst effects. There are poignant signatures of this transition in proxy records. Paleobotanists find a so-called fern spike in the wake of the boundary, a global flourish of ferns and other spore-producing plants that opportunistically colonized, burned, and denuded landscapes. Ferns are ecological first responders. Their spores ride the winds into open ground, and unhindered by the competition of full canopies, they carpet the earth quickly. The image is cinematic, landscapes blackened to the horizon, then pale green with the forked fronds of ferns, a temporary rebound that tells us in plant shorthand that catastrophe had come, and life was beginning its awkward crawl back. Over longer timescales, decades to millennia, the survivors diversified into the empty niches. Small mammals, once living in the shadow of dinosaurs, radiated into forms that filled roles from burrowers to arboreal foragers to ultimately, in a very, very long line of descent, the primate lineage that would give rise to us. Birds, the avian lineage that carried through the boundary, explored new ecologies, seed-eaters, omnivores, aerial predators, aquatic specialists. The Cenozoic, the geological epoch that followed, is sometimes called the Age of Mammals, but that shorthand hides a deeper truth. It is the age of ecological experimentation after an extinction event cleared the stage. This ecological reshuffling unfolded against a backdrop of geological and climatic recovery. The initial impact winter, the abrupt dimming and cooling, was followed by a complex climatic rebound. When the soot and aerosols gradually settled and sunlight returned, Earth did not simply revert to the late Cretaceous status quo. Greenhouse gases released by wildfires, impact-induced volatilization, and, in some regions, volcanic emissions pushed climate corridors in new directions. Oceans warmed, circulation patterns shifted, and ecosystems found themselves navigating a reshaped climatic map. Over tens of thousands of years, sedimentary sequences show switching communities and evolving ocean chemistries. Life adapted not to the world before, but to a new one.
If the biotic aftermath tells us one story, the geological and geochemical records tell another, a detective saga writ large in rock. The modern narrative of Chicxulub is as much about human curiosity and persistence as it is about an ancient rock. In 1980, the Alvarez team, Luis Alvarez, his son Walter, and colleagues first proposed the bold idea that an extraterrestrial impact had caused the end Cretaceous extinctions, pointing to an anomalously high layer of iridium. That observation rippled through the scientific world, like a thrown stone finding concentric circles. The hypothesis was elegant and testable. Scientists immediately started hunting for the smoking gun, the crater. It took years of piecing together clues. Tsunami deposits, shocked minerals, seismically anomalous regions before the Yucatan structure emerged as the likely culprit. Drilling and geophysical imaging in subsequent decades revealed the ringed architecture and the melted rocks consistent with an enormous impact. The discovery of Chicxulub, buried beneath sediment and sea, was an archaeological triumph on a planetary scale. It converted a persuasive idea into a physically grounded event, a moment in Earth's history anchored by a geological scar. But the detective work did not stop at discovery. Scientists set about reconstructing the sequence, the bolide's approach, the impact dynamics, the distribution of ejecta, and the global environmental consequences. They built models of atmospheric circulation to understand how aerosols would have dispersed, ran simulations of re-entry heating to quantify thermal pulses, and used geochemical fingerprints, isotopes, and trace elements to time events and track their after effects. Each new drilling campaign into the crater, each core recovered, added pages to the storybook. The nature of the target rocks, the presence of marine carbonates violently mixed with impact melt sheets, and evidence of a long-lived hydrothermal system where hot fluids, rich in dissolved minerals and chemical gradients, permeated the collapsed peak ring. Those hot vents likely hosted chemosynthetic microbial communities. In the immediate aftermath, a small, stubborn engine of renewal in the shadow of annihilation. Yet the scientific narrative is not a single, unchallenged script. The late Cretaceous was an active, changeable world. The Deccan Trap's vast volcanic eruptions in what is now India were painting significant volumes of basalt and releasing greenhouse gases around the same interval. For a time, these parallel stories fueled a polarized debate. Was the asteroid the smoking gun, or had long-term volcanism slowly strangled ecosystems? Over the past decades, the tone has shifted toward integration rather than exclusivity. Models now often consider multiple stressors, sustained volcanic forcing, that may have raised climatic baseline vulnerability, overlaid by the sudden global shock of the impact. Some ideas even entertain the possibility that the seismic energy of Chicxulub might have temporarily accelerated volcanic activity, a planetary 1-2 punch. The truth, as is often the case in Earth, history is likely a tapestry of interwoven causes rather than a single thread explanation. Beyond the strictly scientific, Chicxulub has an outsized role in our cultural imagination. It is an origin myth for the modern world, the dramatic punctuation mark between two very different biospheres. It appears in schoolbooks as shorthand for the end of the dinosaurs, in documentary films as apocalyptic spectacle, in Hollywood as a reminder that the sky is not always benign. This cultural resonance matters because it frames how society perceives existential risk. The asteroid that slammed into the Yucatan did not annihilate life itself. Microbes and many other lineages endured, but it did erase a dominant suite of forms and cleared the way for new evolutionary trajectories. In that sense, Chicxulub is a narrative parable. Contingencies matter, so do rare events. That parable has practical implications. In the modern age, we possess both the technical capacity to detect near-Earth objects and the nascent ability to consider deflection or disruption strategies. Planetary defense is no longer science fiction. Telescopic surveys catalog thousands of near-Earth asteroids. Space agencies coordinate impact risk assessments, and engineers plan test missions to nudge problematic objects. The logic is straightforward. If the Earth once took a world-altering hit from a kilometer-scale rock, avoiding a second is both feasible and prudent. The specter of Chicxulub thus catalyzes a different human response to cosmic risk, one that leans on observation, international cooperation, and engineering rather than fatalism. There is a sobering humility embedded in the Chicxulub account. The forces that shaped planetary history operate on scales and by mechanisms that can be indifferent to life's struggles. Life's persistence through the most severe global perturbation we can identify suggests that biospheres are tenacious, given time and ecological space. Microbial communities re-established, biogeochemical cycles, plants recolonized barren soils, small vertebrates diversified to occupy new niches. From an ecological and evolutionary perspective, mass extinctions are not only endpoints, they are also generators of novelty. They reconfigure selection regimes, shuffle gene pools, and create opportunities for expansion and innovation. Finally, there is a philosophical echo. Chicxulub invites us to, for a moment, stand outside human time and contemplate the deep contingencies that shaped the world into which our species eventually arrived. It forces a reckoning with causality and chance, a single, relatively small object set against planetary scales of rock and ocean, whose brief passage changed the arc of life. The modern biosphere is an outcome of survival and chance, as much as it is the product of slow, directional change. So where does that leave us? Standing on a planet whose history is written in layers of ash and limestone, in shock-metamorphosed minerals and fossilized bones, we have learned to read a narrative that is both tragic and productive. The Chicxulub impact is a story about sudden violence and long, patient recovery. It is about the vulnerability of specialized life, the stubbornness of the small and generalist, and the capacity of Earth to reknit itself after profound rupture. It is a cautionary tale, a scientific detective story, and an origin myth folded into one. And for our small, self-aware species, the lesson is double-edged. We are the inheritors of a world rearranged by catastrophe, and we are, for the first time in planetary history, capable of learning from that history to reduce similar risks in the future. We can scan the skies, plan a deflection, and build a culture that takes long-term planetary threats seriously. We can also remember that survival is not only about avoiding the next rock from space, but about stewardship and resilience on Earth's own terms. 66 million years separate us from the moment the asteroid met the planet, yet the memory of that meeting is etched into rocks, bones, and the architecture of life itself. The Chicxulub event is a reminder that history, whether human or planetary, is full of hinges where futures split and new possibilities are born. If we listen carefully to the deep time record, we find both warning and encouragement. Catastrophes have the power to end worlds, but they also open the door for new ones. I've told you the science, the drama, and the long aftermath. I've tried to keep the awe without losing the nuance. The story of Chicxulub is a story we inherit, a cosmic interruption that reshaped life's pathways and, in a chain of contingencies that runs to us, made our existence more likely. We are, in a sense, a planetary consequence of a violent, indifferent meeting between rock and water. Remembering that can humble us, motivate us, and perhaps, if we are wise, make us act to protect this fragile, resilient place we call home. I'm Hooper, watching the deep past so we can better steward the future. I'll see you in the next era.